So what I'm going to talk about today, it's about code regulations for seismic design of reinforced concrete wall buildings in Chile. What has been done, the design procedures, and what we are currently discussing these days. So in terms of seismic design codes, we have several seismic design codes. So the first one, NCh433, is for earthquake-resistant design of buildings. So that's similar to ASC7, has some spectrums and other issues. And then we have the NCh430, which is concrete design. So it's about ACI 318. And then we have other documents for industrial facility or base isolation buildings or passive energy dissipation devices, non-structural components, masonry, confined masonry, wood, steel, others. So there's different codes for different materials, the same for bridges. We have a different code for bridges. There's a big concern, though, that each of these codes has different spectra because people in Chile have not been able to agree which is the right hazard for designing structures, and if you compare the design spectrum of different codes, they are different, and it's something that doesn't make sense. But people in the industrial facilities said we need to have a higher spectrum because we need to maintain the operation of industrial facilities. So for buildings, those design spectra are lower, so we have not been able to agree which design spectra should we use. And that's a big concern. So for designing buildings, residential buildings and commercial buildings, we have three documents. One is the first one on the left is for the seismic design of buildings, and then we have reinforced concrete design. And then those two are design codes that are legal. But then we have a new document, which is the one in the right, that is performance-based design of buildings. This is not a code, so it's a guideline, and it is not mandatory. So you cannot design a building with this one on the right. And there has been pressure for not working on this performance-based design because most buildings, like 99%, you don't need to use performance-based design. So why we need to put that much effort in performance-based design if that is only for, I don't know, 10 buildings per year or even less? So a big concern has been put in normal seismic design of buildings. And if you want to analyze the performance, well, that could be in a PhD thesis to analyze how you design normal buildings, and maybe that can provide modifications for the normal design of buildings using common design method and not performance-based design. But we're in the process of developing a new performance-based design code, but that will only be used for maybe 10 or less buildings per year. And also there's an issue, like engineers that we teach in the universities, not every engineer really understands performance-based design. You need to do nonlinear analysis, which is something difficult to do. So why every engineer should do performance-based design? I think we shouldn't teach every engineer for doing that. It's like when you design, for example, a bridge. I wonder if some of you have designed a suspension bridge where you have cables, where you need to use nonlinear geometry for that design. Not every engineer know how to do that, and we shouldn't teach every engineer to do that because it's something you do only in a very few projects. And also it's something about cost. Like if you design a building, there's a particular cost associated to engineer, so you need to do a simple design that is reliable. So if you do performance-based design, which takes a lot of time and a lot of effort and a lot of engineer hours, then there's a problem of how much time you require, what outcome you will have, you will provide, and what is the society is willing to pay for that design. So I think we should need to put a lot of effort in normal type of design using equivalent lateral forces and response spectrum analysis, because that's how we design most of the structures, like 99% of the structures. All right, so evolution of concrete codes. We started in the 1950s. We started using German codes But in 1983, there was a vote between professionals, and they decided that they want to follow ACI-318. And that was the time when the country started using ACI-318, and that was in 1985, we had a big earthquake, and then the NCh433 was published, and then it was updated in 1996, and then that code says, okay, we're going to adopt ACI 318/95, but with some modification. And the most relevant modification is that we don't need special boundary elements for walls. Why? Because buildings in Chile have many walls, so we have redundancy, so we don't need to, the buildings are not subjected to such large displacement demands. All right, and then in 2008, there was a reinforced concrete, a code that was published, and then we have 2010, another big earthquake, the Maule earthquake. Jose went there too. And there were new decrees that were published that updated our codes, and now we are working on updating the 430 code, which is for reinforced concrete, and also the 433, which is for buildings. So we're actually working these days in updating these codes, and we're expecting at the end of this year to have the new version of those two codes. So regarding buildings, so I'm going to say a few things about the two codes, one for the buildings and one for reinforced concrete, but not performance-based design. This is just normal design, is how 99% of our buildings in Chile are designed. First thing is that we promote the use of reinforced concrete wall buildings in the country. Why? Because society in Chile have seen that they have worked good in past earthquakes. We had several earthquakes, so people believe that walls are a good system, so they teach architects that buildings should be designed with walls, and people enter in a building and like to touch the wall and feel that it's strong, so it's just something cultural, like we use a lot of walls, but then the design code promote the use, and I will give some information about that. Base shear is limited by a maximum minimum value, similar to ASCE7, and also interstory drift is limited. So it's limited to 0.002, the interstory drift ratio, which is difficult to compare to the 2% drift ratio of US. So this is 0.2%. But for this verification, we use reduced force, and for estimating the period in the model, we use gross moment of inertia. So it's not a simple comparison with US. It provides stiffer buildings, but not 10 times less. It's the comparison is not that way. Something we do not have, and it's something that we should push, but we have not been able to do that, is to avoid structural irregularity, how to penalize that, how to add more forces for buildings with structural irregularity. And also we don't include P delta effects, because most buildings are kind of stiff, the deformation is not that large, so why do we care about something that is complicated? So we just don't use P delta effect for residential buildings. And then uncracked sections are commonly used in our models. So this is a view of the city. So you see a bunch of buildings over there. The tallest two buildings have been designed with performance-based design, but all of the other ones not. So we do care about, if you think about resilience and risk, you really need to care about all the other buildings that you are designing. And that's where I think we need to put the efforts to modify those. This is a typical residential building that we design. So it has a lot of walls here. You see the walls. And then on the basement, there is usually bigger plant floor for basement, for the parking. So those are the type of buildings we usually have. You see a lot of walls here. And those walls are for dividing apartments between each other. So it's a redundant system, kind of stiff. And that's a typical buildings that we are designing. And some people said we should do performance-based design for this type of building, but I think we should not. I think probably we have to do performance-based design at university, and PhD students, to really make sure that the code works, but then for designing, like a lot of these buildings, I think response spectrum analysis works reasonably good. So analysis procedure, we only have two: equivalent lateral forces, model response spectrum, and almost everybody used the second one. Equivalent lateral forces are mostly used for 1, 2, or 3-story buildings, but not for the building that I just showed. So response history and nonlinear are not defined in the code. It takes too much time. So that's why we are proposing a performance-based design document that will be used, that will use those methods, but only for a very few buildings. So the performance-based design will be introduced in a new code. Strength reduction factor, this is something different on ASCE 7 because, well, it depends on the structural system, the same as SQUARE, but it promotes the use of reinforced concrete walls, but also it depends on the period of the building, which is not the case in the US. So that's the strength reduction factor. So you have the fundamental period of the building that you put there, and then there's an R0 term where you include there to obtain this R star. If you look at reinforced concrete moment frame, you have a value of 11 that you need to plug in that equation. If you have walls, you also have 11. So even though we know that walls have less ductility capacity, but the strength reduction factor that you use if you design a building with walls or with moment resisting frame is the same. So you don't get less shear force for designing a frame structure. And actually you need to then comply to the interstory drift limit, which is difficult. So you need to use big columns, big beams, so you better use walls, because then you have stiffness and then you have the same strength reduction factor, so let's use walls. And that's why this promotes the use of walls. And this is how R factor looks like depending on the period. So it goes to values to about 11 at the most, but then you also have the minimum shear. So then you need to comply with the minimum shear, so then varies you the strength reduction factor that you plug at the end. So I think these things have been debating, and we have been discussing these values in the update. This is the design spectrum, how it looks like for different soil types. And then for load combination, we use a 1.4 factor for amplifying the earthquake loads. And then for estimating displacements, and then for drift, we multiply those displacements by a factor to be conservative. So the displacement spectrum is not compatible to the pseudo-acceleration spectrum because of this CD's factor. So this is how a construction of a buildings look like. So that's the basement, and you see the walls here. So there's a confinement of the wall. So that's the confinement of the wall. So a big concern is what happens if you have a wall with this cross-section. How you deal with, how you design this, and of course how you do a performance-based design with an element that has this cross-section. It's really difficult to imagine if you can model this properly. Jose has done some efforts to model Chilean building, and it's tough because this geometry is really difficult to model. You don't know how it will behave. So that's why linear system works good for this. All right, so now we're working in the reinforced concrete code proposal, and it's not a very long document because it's going to adopt ACI 31819, but with modifications. So it's a short document. It says, use 31819, but with these changes. So for example, this is one example. So modify 4.2.2 with this text. So it just points you what are the differences with 318. For example, seismic design category D should be assigned to all buildings. And then there's another thing that we have, that if you have buildings of 5 stories or less, then you can use ordinary reinforced concrete walls. You don't need special reinforced concrete walls, so you don't need to follow chapter 18. For structural walls, There's a limitation of the thickness. So if the thickness of the wall is less than 1/16 of the clear height, then the lateral instability should be considered. So since there is no guidelines on how to incorporate that, probably the engineers will not do that thin walls. So if you have a clear height of 240, so that means 15 centimeters. So in 2010, we saw 15 centimeters walls that had some damage, so that's difficult to get. So we'll probably have thicker walls than 15 centimeters. ACI limit has that limit, but only for the special boundary elements, but not for the whole wall itself. Then we required 2 curtains of reinforcement. ACI, for example, allows 1 curtain for certain structural walls if you have less than certain shear. Another thing that we have is that if you have a T-shaped wall or L-shaped wall, you should compute the interaction diagram assuming the complete cross-section. And that's because we have weird cross-section, and the cross-section that I show you here, some people are trying to make 3 different cross-sections such that you can analyze them independently, because it's how you do an interaction diagram with that wall. That's something difficult to do. Something that we have included also is we are limiting the axial load ratio in walls. So this is not in ACI 318, but the maximum axial load is limited to 0.35 F'(C)Ag, and that's due to compression failure that we observed in 2010 earthquake. So that's something that we included. And there's concern about non-rectangular cross-sections. Maybe that axial load is still too high. Some people are saying we should even make that value even lower. And then for special boundary elements, now it's something that we have in the Chilean code since about 15 years ago. So the approach in ACI is that you have a curvature diagram, and then using a simplified curvature. I don't want to explain this in detail, but if somebody have worked with this, will understand what ACI does. What it does is assume a simplified curvature at the bottom, and then if the deformation is larger than 3% in the concrete, then you need special boundary requirement. So what we do in the Chilean code is we actually compute that deformation using the equation on the left, which is the same as ACI 318, but also we have an alternative, and that alternative includes that the deformation is not only concentrated at the bottom within the plastic hinge region, but you assume some elastic deformation along the height of the building, because the equation in ACI is very conservative. So that means that we provide less confinement to some of the walls because of that elastic deformation that the walls have along the height. And then the special boundary element, so we need a special boundary element where that deformation that you compute in the concrete strain is larger than 3%. And then for deformation capacity, ACI has some equation that you need to verify that the walls can comply that deformation capacity. In our code, we said, okay, let's check the strain demands in the concrete and in the steel, and that limits are 8% in compression and 3% in tension for the steel. So if you achieve that, that means that the wall will be able to will have enough deformation capacity. So you actually check the strain demands. And that's pretty much an overview. Those are the most relevant changes. I'm not going to go through the dimension of special boundary elements that we have a little difference with ACI 318. And now what we are discussing now is this shear design force, because ACI 318 has some shear design with this dynamic amplification factor that has overstrength factor and a dynamic amplification factor, these two values. This is ACI 318. And now we are actually discussing that, what we should do for our walls. And we are proposing to use like a ductility factor that depends on the displacement demand of the building. If you know where it's located, you know the period, you can estimate the roof displacement, and using the ductility, you can estimate what's the flexural demand in the wall, and based on that flexural demand, we can come out with a overstrength factor for designing walls for shear.